Hello, my name is DDavis. This is a conference paper that I presented in November 2014 at the Internoise 2014 conference in Melbourne, Australia. It describes a method and an example of using engineering optimization techniques to minimize the cost of noise control mitigation treatments. The type of industry is the coal seam gas industry, and the type of noise sources are the power generators and the compressors at a gas compressor station. I believe that engineering can be enhanced by using optimization techniques. If you combine engineering techniques and optimization techniques, then you can increase the overall value of your engineering. This is a schematic that shows roughly the area of viable coal seam gas fields in Australia. It extends from Queensland in the north to New South Wales in the south. This is an aerial photograph showing one of the coal seam gas fields. The small dots are the gas well pads where water is extracted from the ground and the gas escapes from the ground as a result of releasing that pressure. The gas is then carried through to compressor stations where the gas is compressed and the water is collected in ponds. This is an example of a type of compressor that might be used on these types of compressor station sites. A typical site would have a number of these, perhaps 5 or 6 or even up to 10 or 12 of them on a site. Many of these gas compression station sites generate their own power on site using gas-powered engines. The gas engines drive generators which generate electricity, which are then used to power the compressors. So on this site we have 5 power generators. The generators will typically have noise control enclosure around the major noise sources, and these noise enclosures have noise control elements associated with them, including an inlet attenuator where the inlet air is withdrawn into the enclosure, and they have exhaust mufflers, and also the air-cooled radiators can also have a noise control treatments applied to them as well. And the compressors may also need some noise control treatments. So on this site we might have 7 compressors on the site, and the noise control treatments might include, for instance, an enclosure around the major noise sources, and associated with that enclosure there would be an attenuator on the air inlet, an attenuator on the air outlet, and there may even be some noise control treatments applied to the air coolers. So on this particular site where we have gas compressors and also power generators, we might have quite a number of noise sources. There'll be low pressure and high pressure compressors, there'll be electric motors driving them, there'll be coolers for each of those compressors, and there's a number of generators, and each of the generators has a number of noise sources associated with them. So the manufacturers of the acoustic enclosures might have several different options to choose from that achieve different levels of noise reduction and also have different associated costs. So this is a very quick example of combinations. If you have 6 objects and you have 2 choices for each object, then you have a total of 64 possible combinations. If you have 3 choices for each of your 6 objects, then there's a total of 729 options. If you have 4 choices for each of your 6 objects, then there's 4,096 options in total. And just as an example, if there was say 82 noise sources and each with 5 different treatment options, then the number of possible combinations of noise control treatment options is 5 to the power of 82, which is 2 times 10 to the power of 57. So that's a 2 followed by 57 zeros. So that's a very large number of possible noise control treatment options for the site. So I'm going to demonstrate 2 different types of engineering optimization techniques that can be used to select which noise control treatments are applied to the different noise sources. One of them will be SoundPlan's inbuilt optimization module, which was called the Expert System Industry. The other method is a modification of the genetic algorithm. It's called the evolutionary algorithm. Now, it appears that the Expert System Industry optimization method within the SoundPlan software works by calculating the overall cost effectiveness of the noise control treatment options in terms of dollars and decibels, and then the procedure is to incrementally add noise control treatments to each noise source, so the calculation proceeds downhill, so to speak, until the noise limit is achieved at each of the receivers. So it progressively adds noise treatments until the noise limit is met at all the receivers. But the calculation does not appear to be recursive. That means that it cannot backtrack, it cannot allow noise treatments to be lessened in effectiveness in order to allow an overall better cost result. So this is the setup of the noise model in SoundPlan. This is where the compressor station is located, and these are the noise receivers. So this is residential dwellings, and the red markers for the residential receivers are indicating that the noise limit is exceeded at those receivers. Green indicates that the noise limit is not exceeded. So we need to apply noise control treatments to reduce the noise levels at all of these red receivers. So this is a recording of the SoundPlan optimization routine running in real time. It only takes a couple of seconds. There we go, it has finished running. So obviously it's a very, very fast calculation. It has searched through 10 to the power of 57 possible combinations of noise control treatments for each of these sources. And it has very quickly selected appropriate noise treatments for each one, with the aim of minimizing the total overall cost of noise control for this entire site. So this red line is showing the noise level contribution from each source at one of the particular receivers. In this case it's this receiver. And the green line is showing the contribution of noise from each source after the application of noise control treatments. So the sum total of all of these noise sources adds up to less than the noise limit. This is showing the different costs associated with the different noise control treatments. So the SoundPlan optimization routine was recommending the same treatment gets applied to the different sources, which didn't have to happen, but in this case it did happen. SoundPlan recommended that the treatments for this source would cost this much each, and there's that many of them, so the total overall cost is the sum of all of these noise control treatments. The other engineering optimization method that I will be demonstrating is the evolutionary algorithm. The evolutionary algorithm starts with a population of random guesses. It starts by selecting a few of them, and it then creates a whole new population from that group, and then again it selects the best of that population and cycles round and round. That's how it is approximating the law of natural selection, and then at the end of this process it selects the best of the best. This is a recording of the evolutionary algorithm in practice. As you can see, it's cycling through a very large number of options, and it will be selecting the best of each population to move forward into each new iteration. This video has been sped up by a factor of 10, so you see that it's cycled through a huge number of options, and when it converges it ends up at a value that does achieve the noise limit at all of the receivers, and it's chosen the result that achieves that for the minimum cost of all of the populations. So let's compare the two methods, the sound plan optimization routine and the evolutionary algorithm. The sound plan method is not a recursive method. It only considers the cost effectiveness of different noise control treatment options, and it only considers adding them incrementally. And in this example, it gave a total cost outcome of $1,433,600, and it gives the same answer every single time that you run it, because it's quite a simple method mathematically. It only allows you to give a limited number of choices for the noise limits for all of the receivers. So that's a drawback of the method. In comparison, the evolutionary algorithm method is a recursive method. That meant that it can backtrack some noise control treatments for some sources if it gives a better cost result overall. Because it's got some inherent randomness, it usually gives a different answer every single time that you run it, but it does converge to around about the same number every single time that you run it. And one of the advantages of it is that every receiver can have a different noise limit, which can be very valuable in practice. And you'll notice that the recommended result for the evolutionary algorithm method does actually give a slightly better overall outcome than the sound plan method. So the evolutionary algorithm recommended a cheaper noise control treatment program for this gas compressor station site. So thank you very much for watching.